be covering two topics today. The first is verifying differential equations. The second topic will be finding particular solutions to differential equations. Derivatives, comparatively, are very simple. In Calc 1, you can pretty much learn every single derivative rule there is. Product rule, quotient rule, and then all the rules for things like e to the x, natural log, trig, and all that stuff. It covers all of them. There's nothing you cannot take the derivative of. But integrals and differential equations, which are closely related to them, are a whole nother story. We learned one rule, or one method, for solving differential equations so far, and that was the Leibniz separate, integrate, simplify. And that's the only type we're going to deal with in this course. But in college, there's entire classes on different types of differential equations, because there's lots of different methods you can use to solve them, and some just cannot be solved. And that's why we'll learn some methods of what to do if you cannot solve the integral or solve the differential equation. But one thing you can do is, if they give you a differential equation and then they give you a solution, you can test and see whether that solution works or not. And that's really what we're doing here. So in a sense, they're giving us the question, they're giving us the answer, and then we're testing to see whether that answer works or not. So we're just going to do some examples to illustrate that. So this says, determine whether the following are solutions to the differential equation y double prime minus y equals 0. So really what they're asking here is, does this equation exhibit the properties such that the second derivative minus the original function is equal to 0? So we've got several different ones we're going to try here. First one is y equals sine of x. Okay, so I've underlined in red the pieces we need. We need y double prime, so we need the second derivative, and we need y, which is the original. Well, we obviously have the original, y is equal to sine of x, so now we need to find the second derivative. So we start by finding the first derivative of sine, which would be cosine, and then the second derivative would then be negative sine x. So I plug in the second derivative minus the original sine of x, and I set that equal to 0. So all I'm doing is plugging this and this into the original to see if it works. So y double prime negative sine x minus y sine x equals 0. Well, it turns out this does not work. Negative 2 sine x, we're not getting 0 on both sides. If this does work, which you'll see in just a minute, you'll literally get 0 equals 0. It will work the same, the sides will turn out to be identical. So this one does not work. Y equals sine of x is not a solution. Okay, so we were able to verify that this is not a solution. Now let's look at this next one. Y equals 4e to the negative x. Same process, we need to find the second derivative. 4e to the negative x would be negative 4e to the negative x. Remember, the rule for e is itself times the derivative of the exponent. So in this one we just had to multiply by negative 1, since that's the derivative of the exponent. And the second derivative will be positive 4e to the negative x, because we just multiply by negative 1 again. Okay? So when we plug in the second derivative, it's 4e to the negative x minus the original 4e to the negative x equals 0. And hopefully you can see this one does work. 4e to the negative x minus 4e to the negative x is in fact 0. So this one works, and y equals 4e to the negative x is a solution. So without having to solve it, actually do Leibniz separate or some other method on that y double prime minus y equals 0, we are able to find a solution that works, or at least verify that one they gave us did work. Okay, final example, y equals ce to the x. Again, we need to find the second derivative. Well, for this one, the first derivative is just itself, just times the 1, because that's the derivative of the exponent. And then the second derivative is also ce to the x. So we do second derivative minus original equals 0, and this one also works. So anything of the form ce to the x, there can be any constant there, and this one would solve, or would be a solution to this differential equation. So y equals ce to the x is a solution. Now, if you have the worksheet that I handed out in class, this is on page 409 of this worksheet, number 18. And our differential equation this time is the fourth derivative of y minus 16y equals 0. And we're going to test to see if y equals 3e to the 2x minus 4 sine 2x will work, if it's the solution to this differential equation. Okay, so this time we have to find the fourth derivative and the original. Well, we already know the original, it's given, but we've got to find the fourth derivative. So let's get started. First derivative, the derivative of e is itself times the derivative of the exponent, so we need to multiply by 2, 6e to the 2x. Okay, the derivative of sine is cosine, and because of the chain rule, I need to multiply by 2, because that's the derivative of the inside. So I get negative 8 cosine of 2x. Okay, second derivative, I multiply by 2 again, so I get 12e to the 2x. Same idea here, derivative of negative cosine is positive sine, and I have to multiply by 2 because that's the derivative of the inside. Third derivative, it's going to give me 24e to the 2x plus 32 cosine of 2x. And the fourth derivative gives me 48 e to the 2x minus 64 sine of 2x. Okay, so look back through there if you need to. Make sure you understand where all the positives and negatives changed when we switched to sine and cosine, and also what's happening with the coefficients. Alright, so now we try to plug this in. What they're arguing is that if we take the fourth derivative, 48 e to the 2x minus 64 sine of 2x, and subtract 16 times the original function, 3e to the 2x minus 4 sine 2x, that should all equal 0. Okay, well let's simplify and see if that's true. 48 e to the 2x minus 64 sine of 2x minus 16 times 3 is 48. 16 times 4 is 64. And you notice we have two negatives, negative 16, negative 4, so that's positive 64 sine of 2x. And it appears this does actually work. 48 e to the 2x minus 48 e to the 2x. Negative 64 sine 2x, positive 64 sine 2x. So we do in fact get 0 equals 0, and this is a solution. Okay, one more example with verifying differential equations. And again, if you have the sheet I gave you in class, this is from page 409, number 23. Notice this differential equation, xy prime minus 2y equals x cubed e to the x, has some x's in it. Okay, those you just leave alone. Just like the ones we were doing before, you're only going to be plugging in for y and derivatives of y, whether that's the first or second or third or fourth or whatever. So you leave the x's just like they are, and you just plug in for the y and the y prime in this case. So these are the pieces we need to plug in. So thankfully this time we just need to find the first derivative. Okay, so the first derivative of natural log is 1 over x. So I have my pieces. Now I need to plug y prime in, and I need to plug y in. And let's see what we get. X times y prime minus 2 times y. Okay, x times 1 over x is 1, and then 2 times natural log of x is just 2 natural log of x. And those two sides look nothing alike, so this is clearly not a solution. This left side over here should turn into x cubed e to the x if it is going to be a solution. So this turns out that y equals natural log of x is not a solution. So that's the first concept we're covering today, verifying differential equations. The second is finding particular solutions. Okay, so before we do this example I have written here, let me make sure you understand what we're doing. On the previous lesson when we learned how to solve differential equations, we were finding the general solution. The general solution simply means that you're leaving C. You're leaving C as not being defined or found. So if you have a C in the equation, it's the general solution. The particular solution requires that you actually solve for C. And once you solve for C, that gives you the particular solution. So let's try this one. So we still have to go through the whole process of Leibniz, separate, integrate, simplify, and then at the end of all that, we still have to solve for C. Okay, so Leibniz notation, we need to change it to dy over dx instead of y prime. Now we need to separate. I would recommend you move that 3y over first, so add that to both sides. Multiply both sides by dx. Divide both sides by y. And then divide both sides by x. Scroll down a little bit. So divide both sides by x and we get dy over y equals 3 over x dx. Okay, before I take the antiderivative or the integral of each of these, let me say a couple things. First of all, back here, let me highlight this. Back here, I could have divided both sides by 3y instead of just dividing by y. There's nothing wrong with that. You could still get the correct answer. But we know in the step simplify, we're trying to get y by itself anyway. So it doesn't really make sense for us to leave things with y if we can help it, because we're going to get rid of it later anyway. So you can divide both sides by 3y, but I wouldn't recommend it. I would just divide by y since I know I'm trying to get y by itself eventually. Okay? Another thing, you notice at the bottom here, I wrote dy over y, and I also wrote 3 over x dx. So it doesn't matter if you want to write the dx on top or the dy on top, or if you want to write it out to the side. So I'm not going to keep it up here, but just so you know, this would be the exact same thing as this. So these two are exactly the same thing. Doesn't make any difference whether you write those dy's and dx's on top of the fraction or out to the side. Okay? That being said, let's do the integrals. Okay, you should be able to see that both of those are going to turn into natural logs. We get the natural log of the absolute value of y equals 3 times the natural log of the absolute value of x plus c. Okay. We got to get y by itself. We've done Leibniz, separate, integrate. Now it's time to simplify. Okay, e in the natural log of y cancels out to just be y. Now over here on the right side we have two things in the way of our e and our natural log. First is the plus c, and we've talked about before that c can just come down like so. Okay, so we've talked about y. If you want to look at the other video on solving DE, it can explain a little better why. But that c comes down front. Now this 3 is also in our way. So you have to go back and remember the properties of logarithms and what you're allowed to do with coefficients. And if you remember, you're allowed to move them up as exponents. So I can rewrite this as ce to the natural log of x cubed. Now the e and the natural log are right next to each other and to be canceled out, and I'll get y equals ce to the x cubed. So that is my general solution, and that's what we've been finding so far is the general solution. Okay, but now we can use the information they gave us back in the problem to solve for c. They told us that y equals 2 when x equals negative 3. So plug in 2 for y. Oh, I'm sorry, I've made a mistake here. Let me back up. Somebody should have told me. Anyway, back here, when we were right here, the e and the natural log cancel out. So very sorry. This should be c times x cubed, because the e and the natural log cancel out, leaving just the x cubed. So that's our general solution. I apologize for the mistake. So y equals 2, and x equals negative 3. So we get 2 equals c times negative 27, or negative 2 over 27 equals c. Don't stop there. The particular solution is not just the value of c. The particular solution is the equation with the value of c plugged into it. So this is our particular solution. So I know that was a lot of work, but we'd done the Leibniz separate, integrate, simplify part before. The only new part was really just from here down. So the only thing you have to do differently with particular solutions is plug in your numbers, solve for c, and then rewrite the equation with that c value. Okay, if you look in the sections where these problems are found, you've got some practice here. This was what I assigned for homework this particular time. These are all verifying differential equations. And then the last two are finding particular solutions. Just so you know, they've actually already done most of the heavy lifting for you on these last two. So on these last two, they've already found the general solution for you. So all you have to do is plug in the numbers and solve for C.